okay, is equal to negative 82. How much is x? Somebody want to tell me?
0.235.
That much? 0.235?
0.
Yeah, 0.235. Okay. Yeah, yesterday we found 0.2, right? Okay, well,
I think I did it right.
okay, so the,
Oh, we also
Wait.
swaps.
Yeah, I get about 0.8 for, since we did X is the liquid,
okay, how much did you get?
0.795, so 0.8.
So you found 0.8 for the, for the
Mass
vapor?
fraction for liquid.
For the liquid, okay, so that's about right. So it's about 0.2 is for the vapor, right? 0.2 is for the vapor. The book says 0.19, but the book's using the steam tables, okay? So the book's going to be off from what you have by about 5% in this case. It could be even more, but it's 5%, okay? So the mass fraction of the vapor is 0.2? Yeah, the mass fraction, I'm sorry, the mole fraction of the vapor is 0.2, which is also the mass fraction because we only got one fluid. Yeah, what's the thing?
What's more accurate, steam tables or the King Robinson?
I think the steam tables would be more accurate only because the steam tables would have been done from actual data. Yeah, those are, yeah. But on the other hand, I mean, the steam tables, I'm not sure how much of an interpolation already as they put it in, but I'm assuming the steam tables are more accurate because it really does come from actual data. This is, after all, an equation put from the equation of state, okay? So,
Yeah, the number I got is actually 0.74.
that much?
Yeah.
Yeah, I got 0.76 liquid.
Everyone's getting different numbers for this same thing, huh?
Well, I used 105 as a
Okay.
105, 105 plus 7.48, and 83 divided by that number.
82.
Was plus 1 here. You got 1 here. That's what it was.
I got subtract 7.48 from
That's what it
both
was.
sides.
So what do you get?
And then you gotta
82 plus
divide by
7.48.
98.
0.795, yeah.
Okay, 0.795.
Yeah.
And that's what he got. So the answer is about 0.2. Okay, 0.2 is the mole fraction or the mass fraction, as you want to call it. Mole fraction and mass fraction here is the same because it's a single component. So 0.2 is the mole fraction for the vapor, 0.8 is the mole fraction for the liquid. Everybody on board? Okay, so what do we do next? The next part's tricky, yeah.
So, in like real life, this explosion is not going to have this like a change in entropy equal to 0, right?
No,
Okay.
you can't, because you've got all sorts of other conditions. This is the maximum energy of the explosion, okay? In case you have a lawsuit, you know they can't sue you for more than so much, okay? This is it, okay? Ah, well, you know, you may as well make some money being, after learning thermodynamics. I mean, come on, okay? Got to do something with it, right? Okay. Send you all off there to Tallahassee to get some more, okay? Washington, okay? Okay, so we got the mass, we got the mole fraction, the vapor mole fraction is 0.2, the liquid's, we can write that down there.
Oh,
Yeah, yeah, so there. Okay, how do we proceed from here?
Calculate the final
Final what?
enthalpy.
Enthalpy.
So use those values, get the
But isn't it what you want, the final internal energy?
Right.
I mean, you started off with the initial internal energy, don't you want the final internal energy? Isn't that what is going to give you the work?
that was the object. I thought after finding the final enthalpy, you could subtract minus PV, which is molar volume in the gas phase. I would
Okay,
imagine.
okay, good. So how are we going to find the final internal energy or enthalpies and then the internal energies? This is going to be a little,
The mole fraction
times what?
times
Enthalpy.
Enthalpy, let's hear it. The mole fraction times what? Tell me, let's say the mole fraction of the vapor.
of the vapor times the enthalpy of the vapor plus the mole fraction.
Oh, really?
Minus.
Can you just do internal
Let's be
energy?
careful. Let's be careful.
What about internal energy?
How about the mole fraction, correct so far, of the enthalpy of the vapor minus PV for the vapor, plus 1 minus the mole fraction times the enthalpy of the liquid minus PV for the liquid. Okay? You gotta do this really carefully, otherwise you will get the wrong numbers, which is what happened to me yesterday. Yeah, just to let you know, that can happen, right? Yeah, so you've got the mole fraction times the enthalpy of the vapor minus PV for the vapor, okay? Plus 1 minus mole fraction times enthalpy for the liquid minus PV for the liquid. Now, of course, PV for the liquid is not so important because V for the liquid is pretty small, but the vapor V is pretty important. And so when you look at the vapor, you can see this. It's about 3 orders of magnitude larger specific volume than the liquid, and it will matter big time. Okay.
Is that the reasoning behind disregarding it originally?
What's that?
Was that it was a pressurized liquid state, so you can say that PV was relatively. I didn't see a number pop up or anything, so I was just wondering if you could always make that assumption.
Well,
initially,
no.
or
If you really want to be picky about it, you can subtract out PV. But if you know how to subtract out 100, if you know how to subtract 10 to the minus 5 from 100,000, and tell me it's meaningful, go ahead and do it.
That's what I just didn't. How do we know that it's going to be that order of magnitude?
You don't until you plug in the numbers. I mean, that's why.
It spits out the information.
That's why you had 29,734 minus 20 bar times 2.6 times 10 to the minus 5.
Oh, okay. Yeah, right.
Okay, so that's how you know.
Okay. So
And you can plug it in and see the.
It won't matter. Okay.
Right. Okay.
You don't know that in advance.
Yeah. That's. I was like, when can we make that assumption? But I just wasn't.
You never make the assumption until you see the numbers. Yeah.
So your V is specific volume, right?
Okay.
Yeah, these are technically all, specifics.
Yeah, these are all specifics. I mean, or under bar, over bar.
Whatever you're gonna call them.
Okay.
Whatever the mole one is.
Okay. Okay. So you've got. Do you see that? Okay. So let's write down those numbers from what we have here. Now you got to make a conversion. P's in bar and V's in V's in moles per meter cube. V's in meter cubes per mole. And the conversion factor. Oh God, the conversion factor. It's in the beginning of the book. It's 10 to the minus 5, right? Or is it, what is it? Is this 10 to the 5? 10 to the plus 5. 10 to the plus. Well, it's here. It says 1 bar equals 10 to the 5 joules per meter cubed. So you can do everything in joules. Okay, that's what you have everything in. Okay, so you've got to multiply your PV times 10 to the plus 5. Okay? Oh yeah. Oh, I'm sorry. I can see also your question you asked, friend. Yeah. 29,734 is large compared to 20 bar times 2.6 times 10 to the minus 5 times 10 to the plus 5 for the conversion. But 20 times 2.6 is at 52, and 52 is still pretty small compared to 29,734. Yeah, that's so you can see. That's really what the number is. Okay. 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 So you need a 10 to the 5 factor.
Yeah, I'm gonna get that, but there's one other thing.
Yeah.
So it's 10 to the 5, this is the bars, joules per bar.
Yeah.
Is that joules per bar?
What's
What was the conversion again?
it's 1 bar equals 10 to the 5 joules.
Okay. Question is, what specific volume are we using?
For the vapor,
Yeah.
What's the number we need?
3 times 10 to the negative 2.
Yeah.
3 times 10 to the negative 2.
Make sure you get the right one.
Yeah, you gotta be careful.
Bring all those numbers.
Okay?
Somebody get a number. See if I got the same number.
31405.
3-1 what?
31405.
We're close. I got 3179 too. But close enough.
What are the units?
Ends up being joules per mole. This is. All right.
Okay,
Now, what do we have to do now? We only got one step left, right?
what is it?
You multiply times the moles.
Multiply it by the number of total moles that you had in the tank, right? Which is some number out there that somebody
Yeah,
was,
I got it hanging out right here.
yeah, 7,000, whatever it is.
692.
Right, okay? The moles multiplied by the joules per mole gives you the joules, divided by whatever it is.
You need the difference, right?
Right, you need a difference, right?
So we got 29, something like that, 734.
You can expect to have a problem where you will have a fair amount of calculation, okay? So, get used to your computer. And you can go back and work every problem that we've given you so far where you did not have an ideal gas state, and where you had to use this. It's worth, I mean, you don't have that many problems. Turbine, compressor, power cycles, and explosions, emptying tanks, whatever. How many possibilities do you have? There's 5 possibilities or 6 in this course. By now you have mastered them all. Yeah.
What's the topic of our quiz?
What's the topic of the quiz?
Yeah.
I haven't even started to write it down. Boy, I can hardly get through the day. And you're asking, boy, you plan, what are you going to do next year at this, on this exact day? You must have had a plan. I bet you have it out there. Probably, right? Yeah, there you go. Firemen yell at it all the time. Okay. You know, the Russians have this 5-year plans, you know.
They worked very well.
All these.
Depends on who you were.
Okay. Okay.
I'm lucky if I know what I'm doing tomorrow.
Okay, yeah, I am telling you. Okay. Okay. I mean, you could have asked me what's going to be on the quiz. That would have been a better question. Okay. Answer still would have been I don't know. 3 famous. Okay, yeah. Okay, you got that. Okay, is that clear?
15,830. They got 15,772 for
Yeah.
at least interview. Yeah, pretty close.
Okay. Yeah, you could be off by 5–10%. You can't help it. You know, you're using different tables,
You round it
equation
up.
state.
No, how you round.
Yeah, right. Now, we have a couple more problems.
You do a couple more.
Yeah, let's go. Okay.
So, you want to do another one, or you want to?
Okay, so we got a problem here, which is, forget which one was that? It was in the. I didn't write it down.
See, I wrote it down, but I don't have that paper.
That's what I was doing anyway. My appointment's literally 20 minutes. I told
It was one with natural gas.
Sorry, do you know which one?
Let's go to Aaron's house.
It was, I don't remember which one it was. It was one with natural gas.
Can you call him? Ask him when
Yeah, 412. Okay? Yeah, 1 second. Yeah, what's your question?
So, how'd you go from the 2058 to the 15,830?
So, this 2058 is joules per mole. I did it times the moles we have to get joules, and then just divide by 1,000.
Okay? Because you want to find out the energy.
unit conversion.
The energy is not energy per mole, but the total energy. Okay? Okay, 412. And 412 is the emptying of a cylinder containing natural gas. Okay, these are your famous tanks. So the tank has got 70 bar and 300 Kelvin to start off with, and it's exhausted until 3.5 bar. And we want to find out the number of moles of gas withdrawn. So you got it's your famous tank problem. Okay, that's okay. And if you could whip out the thing for methane.
Yeah.
Okay, so here you go. You've got your tank, and it's at 300 degrees Kelvin. And how many bar did I say it was?
70.
70 bar?
70 bar, 3.
Okay, 70 bar.
We have a 0.07 cubic meter tank.
And what? How many?
0.07. Or
And the volume of the tank is
0.7.
0.07 meter cubed.
Yeah.
Okay? And we want to find out how many moles were withdrawn from the tank when this comes down to final state. P final equals 3.5 bar. This is P initial. That's equal
Number
to
moles
T.
and final temperature.
Well, yeah,
We're getting both.
that'll come with the right. Okay? So, can you tell me how you're going to do this? First, huh?
So give me the thought process.
Yeah, we need to have the thinking right. This is a problem you've done before. But in the old days, we looked at the Mollier diagram. I want you now to do it with this. Yeah.
Okay, so look up the entropy for that.
Look up the what? Can you raise your voice?
Enthalpy, look up
The
all that.
enthalpy?
Everything for that.
Oh.
Right? That's what I do.
Okay. Let's.
What's the process?
What's the process?
What are we
Exactly.
looking for?
Exactly. I want the principle. What's the idea here?
Change of what? Entropy's flowing out, so you want to do T final over T initial, R to CP.
No, because it's not, we don't have.
This is
CP.
not an ideal
Oh,
gas.
oh, yeah, that's right.
This is not an ideal gas. Anybody, help me.
Constant entropy?
You bet.
That's what I said.
Entropy.
Yeah, it was in there.
You were saying look up a piece.
She said find everything.
Not the principle.
I want the
just
principle,
observation.
okay?
Yeah, it's in
Yeah,
there.
yeah. Okay, so what else do you need? You need the initial entropy, because the initial entropy is going to be the final entropy. What else do you need initially?
Specific volume.
The number of moles. So you're right, we need a specific volume. You're right. Okay, so let's look at the specific volume and the initial entropy. At 300 degrees Kelvin and 70 bar, it's methane, and fortunately we don't have to do much guessing. It's a single phase. Where are we?
Did it, you want the phase diagram?
Oh, we can if they want to, but I don't think we need it. I think they know by now. It's well, in case you want to know. I mean, it's a good thing to know. Are you in
Did you
in
change
the,
the
in the
compound?
gas phase or what? You may as well see it.
Did you change the compound?
Yes, he did.
Yeah, it's methane.
Yeah, it's methane.
What happened? Oh no, the reason it didn't converge is because you're not. Chase?
Yeah.
The reason it didn't converge is because you're in one phase. Okay?
Gotcha.
Okay.
Yeah, it won't show the line.
Okay, so what phase are we in? I mean, look, he's drawn a diagram from 1 bar to 10 bar, and he doesn't see any red line there. So what phase must it be? It must be a vapor. So good, there you go. Okay, so we are in the vapor phase. We don't have to do much more. Okay? You can see that when you don't see a red line, there's a reason there's no red line. It's okay. You're not in the vapor liquid region in that range. So you must be in the vapors because you're so low of a pressure, right? So now let's calculate the entropy. Can anybody tell me the entropy of what's inside based on what we see here?
Negative
Negative
38.
38.
Minus 38? Yeah.
Doesn't matter between 3 and 6.
Yeah, but it's minus 38.